This is part 2 of a 2-part video series on antiderivatives. So if you haven't seen part 1, go back and watch that video now. And as before, we're looking at two different functions, capital F and little f. If you start with capital F, take a derivative, you get little f. Going backwards, if you take the antiderivative of little f, you get capital F. Now it's time to mention that our notation for antiderivatives that we introduced looks suspiciously like something else that you might have seen, something that's coming up very soon in our course. This thing on the bottom looks the same except it's got this extra a and b attached to it. And they're very different things. On top we have something that we've introduced as an antiderivative, and on the bottom is an integral. Don't confuse them. They're different things. The one on top is a function. The thing on the bottom is just a number. And the relationship will not become clear until after we've covered two important topics, Riemann integrals and the fundamental theorem of calculus. So we'll get there soon enough, but we're not trying to rush into it. However, mathematicians who are well aware of the connection often simply refer to both of these things as integrals. So that's confusing at first. So let me say, by way of clarification, that the thing on top we sometimes call an indefinite integral, and the thing on the bottom we call a definite integral. So a definite integral is some kind of number we'll talk about later. Right now we're talking about something called an indefinite integral or antiderivative, which you can regard as synonymous. This will all make sense later. Right now, just worry about the thing on top. So an antiderivative. And let's practice, again, taking an antiderivative. This is an example. And I want to compare two different ways to work out this antiderivative. The first way I discussed in the previous video. So I'm going to try to guess a function whose derivative is something like cosine of bx. I'm not going to even worry about the constant a out front. Let's try to keep our guess as simple as possible. I can always adjust the constant later. I know the derivative of sine is cosine. So my first guess for antiderivative would be simply sine of bx. So if I try that, I take the derivative of sine bx, and I use the chain rule, and I get cos bx times b. Now we're almost there. The only thing is we'll get the wrong constant out front, which is b, and I want an a there. So just multiply both sides by a over b, and that fixes it, right? b's cancel, and I get what I want, except for the constant plus c at the end, which I have to throw in as well. Now, here's another method, and I'm not suggesting it's better, but in time this will become a very useful technique for you. It's called substitution, and we're going to substitute u equals bx, and you'll hopefully quickly get on the idea of what is the right substitution to use. And the quick rule is you take the inside part of your expression. The inside part of the cosine is bx. And that is what is your new variable u. When you make this kind of a substitution, you have to also change the differential. So dx won't just become a du, but if you work out what the relationship is from taking a derivative, if u is bx, du by dx is b, so you solve and get du is b times dx. Now we substitute all this into our expression for the antiderivative. Bx is simply u, and then the dx you can work out from the previous line. Dx is du over b. So we put that in our formula. Now the a over b is just a constant, so that pulls out, just like constants pull outside of derivatives. Constants also pull outside of antiderivatives. And then what's left is antiderivative of cos u du. Now this is a standard antiderivative, and it appeared in our table in the previous video. So you just look it up and say, oh yeah, antiderivative of cosine is sine. But now the thing is, we have to also remember that u is just a made-up name for something. It doesn't mean anything to anybody else. So we should go back and write the final answer by replacing u by a bx, and that is our answer. And you'll notice it is the same answer we got by guessing and checking. Now let's actually solve a problem using antiderivatives. A lot of our early examples involve distance, time, velocity, and so on. Here's a good one. A rocket launched from the Earth's surface climbs vertically, starting from rest at time t equals 0. Its acceleration at time t seconds is, this formula, a of t is a times cosine pi t over 2t over the time interval from 0 to capital T. Capital T is 1 hour, but I want to write everything in units of seconds for time. So t is 3,600 seconds. The constant a out front is 3 meters per second squared. So I'm using metric units. Determine a, the velocity, and b, the altitude of the rocket at the end of the 1 hour fuel burn that gets our rocket up into outer space. Now at this point, you should pause the video and reread the problem for yourself. Now believe me when I tell you that you are ready to do this problem. It's not rocket science. You actually have everything you need to solve this. Oh, okay. So, yeah, it's a bit of rocket science, but you know how to do it. The problem also is pretty realistic. I want to tell you that I grew up watching rockets lift off, at least, watching them on TV. And it always impressed me. It always inspired me. The biggest difference between this made-up problem and a real-life rocket launch is that our rocket is going just straight up into outer space, whereas most rockets are designed to send a payload into orbit around the Earth. So their orbit doesn't quite go straight up. It begins to arc as it climbs. Our problem has been simplified just to keep everything one-dimensional. I also need to point out that the word altitude simply means the distance above the Earth's surface. The distance above the Earth's surface. It's the height above the launch site in meters. And this is the thing that we call position, S of t, and we're measuring in meters in the vertical direction. Time is t in seconds, little t. Velocity will be in meters per second. Acceleration will be in meters per second squared. And it's standard to abbreviate seconds by the letter S. And our textbook does that. A lot of physics sources do that. I usually prefer to write the longer abbreviation SEC, since letter S is also our position. Now, feel free to write just S for seconds if that doesn't confuse you. And before I go too far, I want to talk about the acceleration formula that I've shown you here, and I'm trying to make it somewhat realistic. The graph is shown here. I'm only showing you for the first 1 hour time interval that this formula applies. And the constant a out front is the initial acceleration. The acceleration when the rocket first starts to lift off is the maximum, and then it declines over time. So the acceleration tapers off during the first hour as the fuel gets used up, and the fuel starts to be spent. Then the thrust goes down, so the acceleration is also going down. Now, to put this initial acceleration of 3 meters per second squared into perspective, let me say that the acceleration due to gravity on the Earth's surface is 9.8 meters per second squared, downwards. The acceleration in this problem is upwards rather than downwards, but our acceleration is also smaller in magnitude, 3 versus 9.8. So it's about a third as much as acceleration due to gravity in magnitude. And if you watch a video of a rocket launch, like I did as a kid, you turn the screen upside down and you compare the acceleration of a falling object, it will appear that our rocket, by comparison, is moving more slowly than you would expect. So it always used to strike me when I was watching this as a kid that acceleration was slower than I expected, and I always thought, how is the rocket going to get as far as it needs to with such a slow start? But if you do the math here, you'll see that over the course of 1 hour, the cumulative effect of this acceleration, which causes the velocity to build and build, will take the rocket to a sufficient altitude and velocity that it will escape the Earth's gravitational field. If you can actually maintain this much thrust and acceleration for an hour, your rocket will be able to coast beyond the outermost planets as far as you want to go. So to start, let's remember that acceleration is the derivative of velocity, so velocity is the antiderivative of acceleration. And we're given the formula for acceleration. I put it in. Now this has exactly the form of a times cosine of bx, or bt, which I worked out before. So I got the answer, and I just put in my value for b into that formula from earlier in the video. Now we need to use our initial condition, that at time 0 the rocket started from rest, which is velocity 0. Using this information, we get that our constant c is 0. And I put that into our formula to give the velocity at time t. This is the general. Now, instead of the general antiderivative, we have a particular antiderivative, which satisfies our initial condition. This is the actual velocity of the rocket at each time during the first hour of flight. So after 1 hour, I plug in capital T and simplify, and I get 2at over pi. And numerically, putting in our values, I get 6875 meters per second, so almost 7 kilometers per second. Now this is certainly faster than the speed of sound, especially at this altitude where sound travels more slowly than it does at ground level. More importantly for us, it is just a little bit more than the escape velocity needed for the rocket to escape the Earth's gravitational field. So it means that at this point, with no additional thrust, the rocket can just keep going and coast as far as it wants, as long as it doesn't run into some other object or a strong gravitational field. Now, part B. Again, the velocity is the derivative of position. Turn it around. The position is the antiderivative of velocity. We just found our velocity and we plug that in. It's got a constant out front which can just pull outside of the integral. Oops, antiderivative. There I go. Now the same techniques to get the antiderivative. Well, it's no harder because this one is just sine instead of cosine. Now I get again a constant which I called c. I probably should have given it a different name rather than c because it's a different constant than in part A. So forgive me there. And we again use the initial condition, which says at time 0, the height was 0. And you use that to evaluate for the constant. Oh yeah, the constant really is different. So remember that when you get this constant c, it's not always 0. It's a good lesson. But I put that constant into my formula above, and I simplify, and here is the position, which is the altitude at time t during the first hour of the launch. And now I evaluate at the 1 hour, which is capital T, which is 3,600 seconds. Simplify it, and I can evaluate it using our values for the constants. And this is the altitude of the rocket in meters after 1 hour. I can write this in kilometers. It's over 15,000 kilometers. Now to put this in perspective, it's about the diameter of the Earth, a little bit more.